Hey guys, my name is Sandeep Patel. I'm a founder of Slotify.ca. In today's video, we're going to learn about time and space complexity. Time and space complexity is a very important topic. If you are a developer, you should know how to calculate time and space complexity. So in today's video, we're going to learn how to measure time and space complexity. What actually is time and space complexity? What is a big O notation? Why we are using that? Importance of input constraint and some example of time and space complexity as we go along. All right, so first of all, let's understand the fundamentals, right? So let's say you have a computer, right? So computer has a limited space, right? The computer comes with the memory, and it can perform number of instruction per second, right? So this is defined in terms of time, and the memory is defined in terms of space here, right? For example, let's say you write a piece of code, right? So your code may take some kind of input or and produce some kind of output, right? So the big O notation says that, like, whenever you write a program, what is your time and space complexity? Like, what would be the worst time and space complexity, right? Um, the reason why big O concerns about the worst time and space complexity is because of this, right? And so their computer has a limited memory and instruction, right? So let's say you are writing a program which take a lot of space, right? Suddenly your computer hangs and you can do nothing, right? Or let's say you're writing a code such that it takes, let's say, long time to run or execute even like a small piece of code, right? So that's not feasible because a computer has a limited instruction per second. Like, for example, modern computer can perform 10 raised to 8 operations, right? And there's a limitation, right? If you exceed that, then there is a TLE error, right? Time limit exceeded error you get. All right, so that's the basic. Let's try understanding the time complexity, right? So as we know, the time complexity is basically how much time your program takes, right? So that is time complexity. Let's take an example here, right? Real example. Let's say that you are given a task to deliver 100 packages, right? And you can choose two ways. You can either have a scooter where you can take one package at a time, and you could have like 100 packages that you can fit into a truck and then deliver at once, right? So looking at this example, you can clearly tell that the truck is feasible, right? Because in one go you can deliver 100 packages, right? Because time complexity is concerned about how much time it takes, right? So truck takes smaller time compared to 100 trips that scooter can take, right? So how do we calculate time and time complexity, right? So whenever you are trying to calculate time complexity of a particular program, you should um, focus on loops and recursion, right? So for example, in this piece of code here, um, let's say this is a function that takes n number as an input, right? So this is an input and it produces output, right? But in this case it's not producing any output, but like any operation that happens you should consider as one unit of time, right? So you have to assume that each operation take 1 unit of time, right? So whenever you encounter a loop, you have to check how many times this loop runs. If it runs for n time, that means 1 into n unit of time, so it takes n unit of time. If you encounter a recursion, you have to check how many times this recursion happen. Is it happening one time or is it happening n times? So depending on that, you can figure out the time complexity. All right, let's move on to a space complexity. Sorry. All right, let's move on to space complexity. All right. Again, we're going to take the same example here, right? So this you're given a task to deliver a package, right? So you can choose a scooter to deliver a package, or you can choose a truck to fit like 100 packages at the same time. So in the space complexity, we're concerned about the memory, right? The space that we're concerned about. So if you have a scooter, it takes only one package, right? So it requires a smaller memory. While if you use truck, it needs 100 packages, right? So there should be a space enough to store 100 packages. So in this example, the scooter is efficient, right? Because it uses less memory, right? In computer terms, we're concerned about using less memory as possible. All right. Once again, how do we calculate space complexity, right? So whenever you are trying to calculate space complexity, we should focus on variables, call stack, and return, right? So for example, this function here, it takes n input, right? Whenever we're declaring a variable, we have to assume that it takes 1 unit of space, right? If there is a call stack, we have to check if it's called one time, it takes 1 unit of space. If call stack is taking n space, then you have to use like n space, right? If return simply returns like 1 unit of space, right? So let's remember that, and let's move on to big O notation. So what is a big O notation? So big O notation is a mathematical formula that we use to calculate time and space complexity that a particular program takes, right? As we know, when we write a program, it takes some kind of input and produce some kind of output. It's not necessary to have an input and output, but we assume that there's an input and it produces some kind of output, right? And each program has a number of operation or statement, you can say, right? For example, in this piece of code here, you can say it has like two operations, right? Or you can say there's two statement inside this function, right? So in big O notation, big O notation only cares about input, right? So let's say if there's an input, right? If your statement, if they are dependent on your input, then we are concerned about that. We don't concern about how many statements we have, right? So we're not concerned about the operations. So we're concerned about time and space this particular algorithm takes. We'll understand this in depth. Let's move on. All right, so let's talk about the constant time, right? So as I said, time and space complexity is basically we're trying to calculate how much time and how much space our program takes, right? Let's take an example. This is a really simple example here. So this function here, right? Basically it has one statement or one operation, you can say, right? So whenever we're calculating time complexity, we talk about the unit time, right? So each statement takes 1 unit of time. So in this case, and big O complexity depends on the input, right? So we're concerned about input whenever we talk about the big O, right? So for example, this function has a input n, and we're just printing the input, right? We're not doing anything crazy here, right? And this statement is independent of input, right? We're just printing, but it's not dependent on input, right? So for example, what I mean by that is, like, let's say if n equals 5 or n equals 1000, right? It doesn't matter when this program runs, we're just printing it one time, right? Even if it runs 5000 times, it doesn't matter. This console log will run single time, right? So that's what we're concerned about, right? So for example, so this program takes 1 unit of space. So let's say that this is a 1 unit of space, right? So let's say this line, this vertical line is a time measurement, and on the horizontal line is the input size, right? So when we supply input n equals, let's say 1000, right? So in here we have, let's say n equals 1000, right? So this is our limit. so this is from 0 to 1000, right? And this particular program takes 1 unit of time. So let's say it's 0, 1, 2, 3, and up to n space, right? Sorry, n time. um, so we mark point here, right? And let's say our input size grows, so we going in this direction when input size grows from 0 until 1000, right? So we get like a straight line, right? Because even if this code run 1000 times, it execute only one console log only one time. And that's the reason why the graph comes straight line, right? And similarly for a constant space, as I said before, we're concerned about variable declaration, return, and call stack when we are calculating the space complexity. So let's say that we, in this vertical line, now we are using unit space, right? So from 0 unit space to n unit space, and on the horizontal line we have 0 to n input size, right? So let's say this is our input, right? And this return statement is independent of that input. It's not like it's returning 1 no matter how many times this input runs, right? Like let's say this input size is 5000. When we run this program, this return statement will run one time. So it's a similar thing here. This is 1 unit of space, and our program, we're supplying n equals, let's say 1000, 5, 10, maybe 100,000. It doesn't matter. It's gonna run for 1 unit of time, 1 unit of space. Sorry. Okay, let's move on. Alright, so we're gonna go quickly here. It's the same thing here, right? We want to find out the time complexity of this piece of code here. So this is the interesting part here, right? So this is our input array, right? And let's say this array has a, let's say that this n equals array size, right? Array dot length. And let's say our array is a size of maybe 100 elements inside, right? So what happens is, in time complexity, as I said before, we're concerned about the loops, right? So how many times this loop runs? So it's running from 0. You can see it's started running from 0 until the array length. And what's the array length? Is like 100 elements, right? So it starts from 0, and let's say this is 100, right? N equals 100. And this console log is within this loop. So let's say that, as we said before, each statement takes 1 unit of time. So let's say this particular statement takes 1 unit of time, and because it's inside the for loop, if for loop is running n iterations, that means this statement will be multiplied into n times, right? So 1 unit time into n would be n iterations, right? So for example, this console log will run n times. So when this function runs, if at that time, if array length is 100, this console log will run 100 times, right? So what I mean by this is, if this is 100, then this console log runs 100 times, so it's in here, right? So if we draw a graph, it goes like this, right? And therefore this is going in linear direction, right? The graph is going in linear direction. All right, logarithmic time. Okay, so once again, we're gonna quickly go through this piece of code. So this code, we want to find the time complexity of this code, right? And this code, we're trying to find the space complexity for this code. So let's look at this code. So there's a for loop that start at, let's say 1 here. Maybe this is 1, right? And it loops until n. So let's say that we have n equals 100, right? But notice this. Let's notice this. This I is multiplied by 2 each time, right? So for example, let's say that for input 100, what happens is when loop runs, so first time it starts with 1, right? And then 1 into 2, so it goes 2, right? And then next time 2 into 2 4, right? And then next time 4 into 2 8, right? So each time it's like doubling, right, until it reaches to 100 elements, right? um, so what happens is that number of iterations are like half, right? um, so because the number of iterations are half, um, it runs like log n time, right? If you take a log of 2n, if for log base 2, it runs n time, right? And therefore if there is a statement inside this loop, it's also going to run log n time, right? And before, if you remember, the linear time complexity goes in a straight line, right? And but because this there is like input size is half, it's going half each time the loop runs, the graph comes like this, right? And for the similar thing for space complexity, right? So in space complexity we're concerned about the variables return types, right? So in this example here, we have this variable here, right? This loop runs log n times, and this variable is mutated log n time, right? Because let's say this statement runs 1 unit of space times log n, the space complexity of this variable becomes log n, right? And that's why I return this returns simply like 1 unit of space, right? It's not doing anything crazy, it's not dependent on input size. But this variable, it does depend on input size, right? And that's the reason why space complexity of this program is log n space. All right, so we're gonna quickly go through the rest, right? In this example logarithmic, we're concerned about time complexity of this function and space complexity of this function, right? So we quickly look at this first loop. So first loop runs from 1 to n, and it's doubling the I, right? So it's a log n time, right? And there's inner loop which runs from 0 to n, which runs n times. So n into log n becomes n log n, right? And because there's this statement inside that takes 1 unit of time, which is multiplied into n into log n, therefore this console log will take n log n time, and the graph will come a little bit upward, because if you look at the linear graph grows straight, right? But because of log n, there is a slight bend in the graph. Okay, let's move on. N square. Okay, again, we're concerned about the time complexity of this code and space complexity of this code, right? Let's look at the functions. So there's a first loop that runs 0 to n. So array length is n. And then there's another loop which is also n times. So n into n square. So this console log will run n square time, right? If you consider console log is running 1 unit of time, into n would be n square. And that's the reason why the unit time, if we plot the graph, this is a unit time versus input size. So when this code runs, this runs for n square. So let's say n equals n becomes n square here, and this is input size n. So the graph bends like this, right? Right. Similarly, 2 raised to n graph goes like this, right? We're concerned about the time complexity of this and space complexity of this. So for time complexity is simply the loop is running from 0 to 2 raised to n. For space it makes like 2 raised to n iteration, and there is a statement inside, so this statement will be multiplied into 2 raised to n iteration. And because console log we consider as 1 unit of time into 2 raised to n times, that means on this side is unit time. So this will take 2 raised to n. So n becomes 2 raised to n, and then this n is just a number, but it could be 1, could be 100, could be 5,000. For space complexity, we're concerned about the variables. So this variable is inside this loop, which runs 2 raised to n time, and that's the reason why this variable takes space of 2 raised to n into 1 unit of space, becomes 2 raised to n space, right? This return is simply returning this variable. So we're not concerned about this, we're concerned about only this. And lastly, n factorial, right? So in n factorial, where we want to find out the time complexity of this and space complexity of this. We're going to plot time complexity on this side, unit time here, and it versus input size. For space complexity, we're going to put unit space here and this input size on the horizontal line. And there's important thing to note. This is a recursion, right? And as I said before, the recursion count towards time complexity as well as the space complexity, right? The way it uses the stack variable for storing the space, and that's the reason why the recursion are considered in the space complexity as well. Okay, so what happens is, let's say this input is equal to 100. So this condition says that when n equals 1, just return once. Otherwise, we're going into a recursion n minus 1 time, right? So for example, n equals 5. So 5 times 5 minus 1, 4. So it's going to run. First time is going to go n into n minus 1, which is 4. Next time is going to come here 4 into 4 minus 1, 3. Then for again it comes here, then 2 minus 1, 1. So it goes in the factorial fashion, right? 5 minus 4 minus 3, 2, 1, and so on. And that's the reason why it's n factorial unit time and n factorial unit space. Alright, so finally, input size constant. So what is this, right? So as I said before, the computer has a limited memory and number of operations it can perform. So let's take an example. Let's say that you have a computer that runs that has 3 gigahertz of CPU, right, which can perform nearly 3 billion instructions per second. So how much is 3 billion, right? So 3 billion, I would say 3 into 10 raised to 10, right? So 3 into nearly 3 raised to 10 raised to 10, right? So that many operations it can perform. So now what happens? Let's say that you take n input size 10 raised to 5, right? Let's say you are given n equals 10 raised to 5. And if we choose to use order of n square for our algorithm, so what happens is 10 raised to 5 input size plus there's an n square here. So we're multiplying 5 into 2. So we're reaching 10 raised to 10 operations, right? So we nearly reached to 10 raised to 10 operations. So we cannot use this O(n) square algorithm for our computer, right? Otherwise we might get TLE error, right? But let's say if we are not using O(n) square, but our solution is runs on O(n) algorithm, right? In that case, let's say if you're given input size n 10 raised to 6, and because our algorithm runs O(n) times, which means it's going to run 10 raised to 6 operation, so which is within the range of 3 into 10 raised to 10, which means in this computer we can easily run O(n) square algorithm without any issue, right? And which might take like 0.3 millisecond. And this chart, what it shows you here, that okay, if we have an input size n less than equal 10, then our algorithm should use either n factorial or in worst case 2 raised to n, right? So in worst case n factorial or 2 raised to n, right? If we are given input size less than equal 20, so our solution should be either 2 raised to n or n raised to 3. So that's the worst case, right? But if we come up with something better, like let's say instead of 2 raised to n, if you come up with o time 1, right, order of 1, then that's a really fast solution. um, so basically this is it. So this constraint, and this is the worst complexity that we can come up, right? If we are using this complexity, that's fine, because this is like worst case, and this complexity are better than this one, right? So less is better, right? If we come up with our algorithm comes like always in like o1 and log n, that is really fast, right? Compared to all others. So I think that's it. I really hope you guys really enjoy my tutorial. I'm gonna be creating more videos on data structure, so please stay tuned, do like and subscribe. Thank you.